Are we okay?
Yep.
Good to go.
Everybody wishing to attend this new issue of the Physical Review Journal Club for the Physical Review Fluids is admitted, I hope. So we can start. So welcome everyone. So yes, this new issue of the Journal Club is dedicated to recent paper on strays in air called growth of respiratory droplets in cold and humid air. A short presentation of about 15 minutes will be given by his first author, who is Chong Shen Ng. I assume he will present his co-authors. And just before I leave the floor to him, I would like to remind him that he has been advised to emphasize the physical principle underlying his interest in study and its originality in this respect. I'm sure he will do that. So Chong Shen, it's yours.
Great, thank you so much. I'll share my screen. And there we go. Great. Okay. All right, good day, everyone. And thank you for coming to my talk. So my name is Chong Shen Ng. You can call me CS. And this is a joint work with Stephen Chong, Rui Yang, Morgan Lee, Roberto Verzico, and Droplet Counts. And as Emmanuel introduced, I will tell you about the topic of our paper, which is on the growth of respiratory droplets in cold and humid air. And here I've left the reference to our article here. So as everyone is quite well aware, we are in the middle of a pandemic and hopefully recovering from it. So what are some of the lessons that we can learn from the pandemic? Well, to do that, we can actually go back about 100 years. And as it turns out, this article written by Major George Soper has already listed some empirical guidelines back then, but let's have a look at what can we do to prevent a pandemic. So here, there are quite a lot of them listed, but what I want to focus here specifically is on the fluid physics aspect, which is there is danger in the air in which these infected individuals cough and sneeze. So what do I mean by a danger in the air? So this comes in a form of droplets and aerosols. So here I'm showing pictures which are taken by the group of Lydia Baruba and co-workers. Image on the left is a long exposure image of droplets, which are shown by these green trajectories overlaid on this turbulent path. As you can see, these droplets can go in various directions, and the path itself can propagate quite long distances. For instance, the image on the right shows that it is expelled between 7 to 8 meters in distance. So under what conditions do these droplets or path can become dangerous? Well, in order to answer this question, we turn to numerical simulations. Specifically, we perform direct numerical simulations where we have fully coupled droplets and a turbulent path. So using this setup, we can track every single droplet in space, time, and size under very well-defined conditions. So for example, what we can track is a history of a droplet count versus distance or time. Some of the questions that we can pose based on this setup is, for instance, what is the effect of the turbulent paper path? And this is what we published earlier this year in Physical Review Letters. In fact, the topic of the investigation of a vapor puff and its influence on droplets is not new. And in fact, there's a beautiful work done by Emmanuel Villamor and co-workers where they have a very precise experiments where they track the evolution of the droplets and their lifetimes in an evaporating and dense spray. And what they show in their work is that the mixing of a vapor field sets the droplets' lifetimes. So I won't go into too much details of their work, but I encourage you to refer to these two papers. So effectively, the point is it is a mixing problem which drives the droplet lifetimes. So the second question that we could ask is, what are the influence of ambient conditions such as relative humidity and temperature on the droplets? And this is the topic of the talk today. Finally, there is also the question of the effect of ventilation, and that is a topic of ongoing investigations in our group. In terms of the setup, we now have a turbulent vapor puff, which we inject on the left, into a domain where we have an inflow plane on the left side and an outflow on the right. The inlet Koff profile has three components, which are the velocity, temperature, and the vapor field. And these values that I've shown here are the values taken from experimental measurements in literature. So since we have a temperature and vapor field and they are active scalars, that implies there's also a buoyancy component in the turbulent vapor puff as well. In terms of the droplet distribution, that topic itself is a topic of active investigations in various groups. For the purposes of our simulations, we use the experimental measurements of Duguid in 1946, as you can see by the triangles as shown here. And we prescribe an initial distribution, which roughly follows distribution in Duguid. So for completeness, I'm also showing the governing equations for the droplets. Specifically, we employed the Euler-Lagrange approach to simulate point-like droplets. The momentum equation is the generalized Maxey-Riley equation. And we have a two-way coupling of the droplets and the field in terms of the temperature and the mass. And finally, to close all the equations, we have Rance-Marshall correlations here. Of course, all these simulations come at a price. And to put some numbers into that, each case has about 402 million grid points. It takes about 2 weeks to run each case, and we have 12 cases in total. So now on to some of the physics. What is the role of the ambient temperature in this setup? Well, to do that, let's have a look of a video in a warm weather conditions. Here we have an ambient temperature at 30 degrees Celsius, at the relative humidity, which we fix at 90%. And I will play this video now. The three fields that I'm showing in this video are firstly the local relative humidity field, which has an ambient value of 90%. These are the black regions as you see here. Secondly, you have the droplets, which are propagated in the domain, and they have been color coded according to their sizes. So green being the smallest and red being the largest. And as you can tell, most of the larger droplets tend to sediment at the lower plane. And we also have the droplet diameter histograms as a function of space and time on the bottom. So the main takeaway point from this video is that the local relative humidity field in the background rapidly dissipates to the ambient values, which is 90%. As you can tell, towards the end stages of this video, most of the values and the background is almost 90%, it's almost all black. So let's have a look at what happens if we decrease the temperature. So the next video I will show is a video for cold weather conditions. So the ambient temperature here is 10 degrees Celsius, and the relative humidity is the same at 90%. I'll play this video. So note that the three components here are the same. We have the three values. The range is exactly the same. But the key difference between this video and the previous one is that the vapor field, the local relative humidity field in the background persists for much longer durations, and they are actually much, much larger. And the values themselves are much higher than 90%. And I'll play this video for a couple more seconds. All right. So to summarize, when we compare between the warm and cold weather simulations, the key point is that there's a difference in the coherence of this path, specifically the local relative humidity field. So then we ask, how does it affect the droplet counts? Well, to do that, we just have a closer look at the size distributions of the droplets. So here I will show the droplet counts, which is on the vertical axis versus droplet diameters at a time of 1.2 seconds. This black line is our reference initial distribution for all of our cases. At the warmest temperature, which is 30 degrees Celsius, the droplet counts themselves are actually far lower than the initial distribution. So clearly here, the small droplets rapidly shrink at the higher temperature values that we simulated. When we decrease the values of the ambient temperature, we see that these droplet distributions are actually much closer to the initial distribution, which is the black line. And in fact, if we look more carefully, we can see some of these values can be slightly higher than the reference initial distributions. Let's zoom in and look at the smaller droplets, for instance, the 15 micrometer droplets, and ask how do they actually evolve with time. So here we show a time history of the droplet surface areas for sizes of 15 micrometers as a function of time. And this we pick the ambient temperature of 20 degrees Celsius. For most of these droplets, we see that some of them actually are much larger than the initial diameters. So their values here are the normalized values are much larger than 1. And after some time, they actually reduce in size. When we decrease the temperature to 10 degrees, we see that the droplet diameters actually grow quite substantial. Droplet surface area grow quite substantially in the early stages before they actually evaporate. So the question is then, why do at the initial stages, why do these droplets grow instead of shrink? Well, it turns out that the explanation for this comes from the local fluid properties at the location of the droplets. Specifically, the local relative humidity for this case actually exceeds 100% at the early stages of the simulations. So these conditions actually drive the condensations of the vapor field at the location of the droplet, which drives droplet growth. So the relevant parameter here is the local relative humidity field at the droplet. The physical explanation for this is that cold air can just contain less moisture than warmer air. So for the colder case, we get the growth of droplets. In fact, this phenomenon is actually quite well known from daily life for our friends and colleagues in the Southern Hemisphere, where they are going to experience winter pretty soon. In the cold and humid weather, you exhale this white mist or white smoke. And that's effectively the condensations of the vapor field onto the droplets emitted from your breath. So now we know that the local relative humidity field is an important parameter which drives the droplets growth. Can we actually model the local RH? Well, to do that, we refer to the visualizations that we showed earlier and have a look at this expulsion field. So based on this, we can make an assumption that it's a quasi-stationary jet field. And secondly, we know that the local relative humidity field is a function of the fluid temperature at that location, as well as the vapor mass fraction. This means that if we have an expression for this, the fluid temperature and the vapor mass fraction, based on the assumptions of a quasi-stationary jet, we should be able to recover the local relative humidity field for various combinations of ambient values. So in fact, if you just refer to some textbooks, there is an expression for the scalar field in the axial coordinate, normalized by its inlet condition, and it follows this rather neat expression on the right. So once we adopt this expression for both the fluid temperature and the vapor mass fraction, we can reconstruct the local relative humidity field in the axis of this path. So let's have a look at some results for this. Here I'm showing the model that we have, and they are the darker red, green, and blue lines. And the next results are the DNS results, which are these oscillating components. And here we see that the agreement is fairly decent. Okay, of course, up to a mouth distance of about 25 units, the model actually departs from the numerical simulations, and this is expected. Right? The reason for this is the model assumes a fully developed jet, whereas what we have in our simulations is a quasi-stationary jet, which is effectively a path in this instance in time. We can take this model even further and map out the maximum local relative humidity fields as an indicator for instances where droplets grow. So what do I mean by that? Is to take the maximas of our model, for instance, these circular points that are highlighted here, and we can extend this model for a range of ambient relative humidities and ambient temperature. And what we get is a map of ambient relative humidities versus ambient temperatures And anywhere on this point where the maximum local relative humidity exceeds 100%, that is an indicator that droplets should grow, will grow. So when we performed additional numerical simulations and we marked out the instances where droplets grow, these are indicated by the circles in this plot, whereas the crosses indicates that droplets actually just shrink for this space. And as it turns out, our model quite accurately predicts the results in our simulations. So that's a nice result. So to conclude, we found that droplets not only shrink, but can grow in humid and cold air. These growth processes are driven by local conditions, specifically the local relative humidity values. We can predict the local RH by assuming a quasi-stationary jet field. And we extended this knowledge to map out the conditions under which droplets can grow, which are indicated by the circles, or where they just purely evaporate. With that, I'd like to conclude my talk, and I'll be happy to answer any questions from the audience.
Thank you. Thank you, Chong Shen. You have emphasized the physical principles. Very good. Now, if anyone has a question, he is welcome to ask. I don't know how to proceed. Maybe you just raise your hand or drop a line in the conversation, the chat window, or simply speak. Everybody will hear you. So is there any question? Actually, I have a question for you. So you have, one of the results of your DNS is that the instantaneous relative humidity field is extremely noisy.
Yes, yes.
So this is an interesting observation. However, yeah, exactly, this graph. Yes. However, the Lagrangian trajectory of your droplet diameter is extremely smooth. So you have described that it increases, then decreases, but the trajectory, I mean, the diameter versus time is much smoother than the relative humidity field it experiences. Do you have an explanation for this?
Yes, so I have two explanations for that. So firstly, the diameters which I'm showing, which are 15 micrometers, they quite faithfully follow the path quite well. So they remain within these regions and they do get influenced more as compared to droplets with larger Stokes numbers, which can cross this intermittent path. And I guess secondly, the other explanation is that when I show these curves, for instance, these ones here, you can almost see, because these are, for example, maybe a few hundred droplets all lumped together on a single plot as a heat map. So if I were to trace out a single individual line, you can see that these trajectories can be actually a bit, there's one line here. So it's actually quite intermittent. So on a mean sense, it looks smooth, but individual statistics are quite noisy.
Okay. Okay, so the individual trajectories are not smooth, as is the relative humidity field.
Yes.
Okay, interesting. Any question from the numerous audience?
There's one in chat, Emmanuel, from John Hinch.
John Hinch. So John Hinch is asking the following: is the growing drop moving through stationary vapor, in which case the momentum equation for the particle needs a term?
Okay, I'm reading the question now. Is the growing drop moving through stationary vapor field? So there's sort of like two parts in that question. For the first part, the vapor field is not stationary. It's actually evolving in space and in time. And in which case the momentum equation for the particle needs a term. I don't understand what you mean by term, but if I were to flip back to the governing equations again, maybe you could ask. So we have your drag term effectively here. You have the third term here is due to the weights of the droplets, so they can actually sink and fall. And the first term here is more or less the added mass term. So I think all of these should be sufficient to fully describe the motions of the particle.
Can I speak?
Sure.
Yes, you can.
Okay, that equation for the particle motion is correct if the mass of the particle remains constant. But if you're increasing the mass at constant velocity, you're giving it momentum. And
Yes.
you have to say, where does that come? Otherwise, rockets don't work.
Yes. So this equation for each particle will also be updated with time. So the mass itself, so the radius will change with time. Is that your question?
I'm very worried that you are wrong there, but it will be too long for me to explain during a seminar. Go and think about the rocket effect.
Sure. I'll be happy to discuss it offline as well. That's fine with me.
Okay, thank you, John. We have another question in the chat by Professor Balachandar. Do the droplets evaporate fully over a longer span of time? I don't know what longer refers to, but
yes. So I understand what his question is. We actually have to set a lower limit to our droplet size, because actually you can see here there's an R squared term. If the droplets just vanishes, then this term blows up. So numerically, we impose that the smallest droplet size that we have is 5 micrometers. I hope that answered the questions.
Professor Balachandar will tell. Roberto Zenith has a question. So to clean air from droplets, you need hot and dry conditions, correct?
That seems reasonable, yes.
Or you need to filter the droplets. It works also. Another question, I think you can read the question, right? Can you please comment on the dispersal? Yeah, the question on the dispersal from a point of exhalation of the droplets in outdoor settings in the presence of mild air currents.
Yes.
A vast program.
Yes. So yeah, that would be okay. So my take on that is in summer settings, depending on the temperatures, the droplets will get carried away. And if you are in, I guess, lower relative humidity conditions, then I would say they evaporate relatively fast, and you effectively get scalar dispersions of your droplet fields. I hope that's enough as sufficient as a comment.
Okay. There is a question regarding the Maxey-Riley equation. And maybe you can read it.
I see. One is 2 questions. One is any reason to remove a history force in the Maxey-Riley equation? As I understand, the history force is more relevant for light particles. So if your density ratios of your particle to your carrier fluid is smaller than 1, then the history force is more appreciable. However, yeah, I need to check that, but I think that is the explanation for that. Secondly, the second is any influence of drag change due to humidity, in brackets, moisture, as the viscosity depends on RH. Yes, so what I think you mean is this term here, the second term here, this, what we have assumed is that it is a surfactant loaded droplet. So here we assume the no slip condition for this droplet. However, in some more precise modeling, you could, in principle, use the Hanaman. There's a specific formulation for drag where you take into account the viscosity differences between the droplet and the liquid. I'm aware of that, but for this case, we just assume that the no slip condition for the droplets. I hope that is sufficient to explain your questions.
Next, there is a question regarding coalescence between droplets.
Yes, so we did not consider coalescence because the droplet loading here is very, very dilute. So it's less than 0.1% or even smaller than that.
Yeah, and they have the Stokes number, and the droplets are following the flow. Basically, they behave like passive scalars or close to.
No, only for the smallest ones that we have. Maybe very close. Yeah, but we have a range of Stokes numbers. Can go up to a few hundred.
Yeah.
Yes.
Okay. We still have a couple of minutes for this discussion session, so feel free to ask anything. Eric Lauga had a question. No, he hasn't.
He has not.
Yeah, I have another. Let's go back a little bit. There were many technical questions. Let's go back a little bit to the phenomenology. So you have initiated your simulations with the Duguid droplet size distribution. You could have made other choices. I imagine that you have done that because although you're doing numerical simulations, you want to claim that you speak to the real world. I understand that. But you could have investigated other kinds of droplet size distribution initially. Do you think that your conclusions are sensitive to the choice of the initial shape of the droplet size distribution, or are your conclusions essentially independent of it?
Yeah. So this is my opinion. I also, of course, need to understand what my other authors think, my other co-authors think. So my opinion is the conclusions will remain pretty much the same. And the reason for that is we have very dilute number of mass loading of droplets in this case. So for instance, if we were to initialize all our droplets at 15 micrometers and reran our simulations, we would effectively reproduce our results quite closely. But we will not be able to see the influence of the other droplets and how they evolve in time. So I had this plot of an initial droplet droplet count versus time. If I were to just pick one dot and just pick 15 micrometers, I can just see that shift to maybe a slightly broader distribution. That's the effect of, that's the results of it. But it's the same outcome. I think you'll be the same conclusion.
I think I will agree with you. We have a question regarding salinity or the content of mucin in the droplets, and the question is, how does it affect the time scale of evaporation?
Yes, that's a very, very good question, and it's also something that my colleagues in physics of fluids group here are actually doing. I recall that under certain combinations of temperature and relative humidity, the mucinous or the salt will form a crust on the droplet and actually prevent further evaporations. And there's like a very specific combination of parameters which can lead to that. So I guess that for those cases, the evaporation time scale may be delayed. And I think maybe my co-authors can put in a reference to that paper. It's on arXiv at the moment, and you could refer to that one.
Okay. Maybe this is the last question. If the velocity of the puff changes, do you think the velocity will influence changes in the ambient relative humidity field.
Yes, that is actually indeed quite true. The if you increase the Reynolds number of the puff, you effectively have more shear and stretching of the puff, and you will get a change in the rate of dissipations of the puff.
All right. There's a question by Alfredo Soldati on the monodisperse character of the distribution, but I think you've answered to this before.
Yeah.
So
Sure.
Since we're at the end of the discussion session, I have been asked to close this journal club issue. Not after thanking you for your interesting talk, thanking all the persons in the audience, and thanking those who dared asking questions. I'm sure many questions were hidden, but the discussion will probably go on later on. Beverly McKeon may like to say a final word.
Thanks to all.
Thanks to all.
Have a good day, everybody.
Thank you.
Thank you very much. Bye.